Hello, everybody. Today we're going to talk about yet another quite interesting sampling-based path planning algorithm called the potential RRT star. That's presented by me, Ashraf Faraj, on January 2024. As usual, the project is to find a collision-free path from this point right here, the start point, to the goal point, trying to avoid the red obstacles. Now, the figure here shows the two algorithms that we're going to try to merge actually in this video. Now, on the left, you have the RRT algorithm. We have discussed this one in an earlier video. It's a sampling-based path planning algorithm. And on the right is another quite interesting path planning algorithm. It's called the artificial potential field. So the idea of the artificial potential field, which I've discussed in another video as well, is to assume that the robot is actually a point mass moving towards the goal under the influence of two forces, an attractive force trying to pull the point towards the goal, and a repulsive force trying to push the point away from the obstacles, as can be seen here. Now, the problem with the artificial potential field algorithm is that it's actually quite susceptible to falling into local minima. That is, we could find ourselves stuck in a position where the forces cancel out, and this might cause the robot to just stay in place and not be able to reach the goal node. However, one quite interesting thing about the artificial potential field is that the forces that the robot can be subject to can actually give quite an important information that could help to guide the expansion process of the RRT, which could help it actually converge faster. That's the main idea of the RRT star potential algorithm. Now, the figures here show us an example of a path generated by the potential RRT star algorithm on the left and the traditional RRT star to the right. Now, these pictures are actually taken from the main reference that I used in this video, which I'm going to put in the description box. Now, as we can see here, it can be seen that the edges of the potential RRT star are actually more focused towards the goal as compared to the ones with the RRT star. As we can see here, there's a lot of unnecessary exploration to areas not at all relevant to reaching the goal. But in the potential RRT star, we can see that the edges are actually guided towards the goal in a focused manner, while also trying to avoid the obstacles. Now, this is the basic idea of the potential RRT star algorithm, in which we are going to use the potential field created by the goal node and the obstacles to try to guide the expansion process of the random tree. Now we are going to discuss the RRT star potential algorithm in detail. First, as usual, we're going to initialize the nodes and the edges, then the tree, then the cost array, and then we're going to repeat the following steps for a maximum number of iterations nmax. First, we're going to sample a random sample from free space. And now that is the main step in the RRT star potential algorithm, where we're going to take our newly sampled random point and apply the function randomized gradient descent. Now this has the idea of biasing the random sample towards a decreased potential. So we're going to discuss the randomized gradient descent function in the next slide. Now this will give us a point xprand. Now we're going to apply all the classical steps of the RRT star algorithm, which is finding the neighbor within a radius r on xpbrand, sure. Then again, we're going to choose the parent from the neighbors for xpbrand, the newly biased random point. Then we're going to rewire. And as usual, if the newest node is in the goal region, then we save the goal index. And finally, we return the path if found. And now we're going to discuss the randomized gradient descent function, which takes a random point xrand. Now the figure here will help us illustrate the idea. So assume that the random point that we just sampled is here, xrand, the node in blue. Assume that the goal is this one, the green node, and the red is the obstacle. Now the obstacle is going to create a repulsive force that's going to affect each and every point in the surrounding space according to a certain law. And the goal is going to create an attractive force that also affects each and every single point in the space according to a certain law, usually a linear law. Now, the direction of the attractive force would be from the random point to the goal, and the direction of the repulsive force would actually vary according to the shape of the surface of the obstacle. In this case, it would be just along a line joining the center of the circular obstacle and the newly joined random point. So once we compute these both, the forces, the attractive and the repulsive forces, depending on the obstacles and the point location and the goal location, we will arrive at something called a total force, which would indicate to us a direction that in which if we moved, we're going to decrease the potential function created by both the goal and the obstacles, which would hopefully guide us towards the goal in the long run. Now, once we computed this total force, F total, we're going to create another point, which is called XP rand, which will be in the direction of F total starting from X rand. So we're going to take a step, let's say step size of size alpha, in the direction of F total starting from X rand. So in code, this will look like this. First of all, we're going to use a function which is compute the gradient potentials at the current point, which is X rand. Now the type of potentials that we're going to use can actually be varied a lot. I'm going to just put a reference in the description box to the type of possible potentials that we could have used. Now this will give us two gradients, the attractive and the repulsive. Now the total force would be the negative of the sum of the gradients, and the XP rand would be the random point plus an alpha in the direction of F total. Now notice here that we normalized the F total force, just to create a normalized fashion of how to move in this direction. Now to the results. Here on the right, you can see the figure that shows us the results of applying the RRT star potential algorithm on our example. Now, as usual, we can see that the algorithm achieved an optimal or a near optimal path, which is quite expected since it depends on the RRT star algorithm. Now, one thing to actually notice is that the edges in this region are all biased towards the goal. So we can see that the tree in this case is actually more focused towards expanding to the goal and trying to avoid the obstacles as much as possible. So we might expect that the RRT star potential actually achieves faster convergence and actually finds the goal in less time. Now we're going to verify that by doing further studies and comparing it with the RRT star. Now here we show this comparison. Now, as usual, since both algorithms depend on random sampling, we can just arbitrarily compare two trials on this path planning problem. We're going to use different trials and just average the costs on all of those trials. So in this case, we used 100 iterations or 100 trials, and we fixed the number of iterations after reaching the goal to 1000 so that we could have vectors of constant length and just compare them. So we can see here that the potential RRT star actually achieves a slightly better convergence rate than the RRT star algorithm, though their performance is actually quite comparable after many iterations. It could be seen that the potential RRT star beneficially accelerates the convergence rate of the RRT star. But the key idea to note here is the mean number of iterations to find the goal, which is the time that we actually take to find the goal for the first time. The RRT star took nearly 177 iterations. The RRT potential took only 97, which is a staggering difference. Now, the main idea here is that the RRT star potential was actually able to guide the search in a concise manner towards the goal because of the influence of the attractive force and the small influence of the repulsive force that actually tries to push it away from the obstacles. Finally, in this project, we discussed the RRT star potential algorithm in detail. We implemented the RRT star potential algorithm on the path planning problem for a kilobot trying to avoid circular obstacles. And we achieved an optimal or a near optimal path quality. And finally, we compared the RRT star potential to the original RRT star. And we found that the RRT star potential achieved a faster convergence rate in a slight manner, and that the RRT star potential was able to find the goal quicker for the first time, nearly beating the RRT star with approximately 70 iterations in our case. That's it for today. Thank you for listening.